In this week's lecture, we will continue talking about Monte Carlo integration and wrap up this topic. First, let's do a recap. Last week, we introduced the simple Monte Carlo estimator. In order to estimate the bounded integral theta, which is equal to the integral from a to b of g of x dx, we can use the simple Monte Carlo estimator theta hat, which is given by b minus a times g bar of x. Here, g bar of x is the sample mean of n uniform draws from the uniform distribution between a and b. We further showed that the theta hat obtained this way is unbiased, meaning that the bias, which is equal to its expectation minus the true theta, is equal to 0. It is asymptotically consistent, meaning that as the sample size goes to infinity, the probability that our theta hat, the estimator minus the true theta, the distance between the two exceeds some arbitrary constant epsilon, goes to 0. We also showed that the theta hat obtained this way has standard error that is equal to b minus a divided by square root of n times sigma, where sigma is the variance of, is the standard deviation of g of x under where x follows the uniform distribution between a and b. And we further showed that by the central limit theorem, the theta hat is asymptotically normally distributed, and we can use that to establish a confidence interval for the true theta based on the estimates of the thetas that we get. So, as I mentioned last time, there is another important property of estimators that we haven't touched on, and this is the efficiency of estimators. In general, the efficiency of an estimator can be evaluated using the mean squared error, or the MSE. The MSE of a theta hat, which is used to approximate a true parameter theta, is given by the expectation of the square difference between the two. So if we have two estimators for theta, so theta 1, which we obtain using one way, and theta hat 2, which we obtain using another way, then we can compare their relative efficiency by taking the ratio between their MSEs. One thing to note here is that smaller MSE implies that the expectation of theta hat minus theta squared is smaller. This implies that there is lower expected deviation of our theta hat from the true parameter. Thus, the smaller the MSE, the better. We say that if the MSE is smaller, then the estimator is more efficient. So in general, here's another fact about MSEs. The MSE of an arbitrary estimator theta hat for a true parameter that we're interested in estimating theta is equal to the bias of theta hat squared plus the variance of theta hat. So this is known as the bias variance decomposition of the MSE. And the bias of theta hat given over here without the square is just what we have learned earlier, which is the expectation of theta hat minus its true value theta. So this is really not hard to show. You can show this by expanding the MSE of theta, which is equal to theta hat, which is equal to the expectation of theta hat minus theta squared. And by adding and subtracting an expectation of theta hat here and expanding this, you'll be able to show that the MSE of theta hat is exactly equal to bias squared plus the variance of theta hat. I have included a link for the proof for this over here. So if you're interested in this, feel free to click on the handout, and that will lead you to a proof for why the MSE is equal to the sum of these two things. So you can see, since the MSE is equal to bias squared plus the variance of the estimator, if we have unbiased estimators, then the first term, bias squared, will be equal to 0. For example, our simple Monte Carlo estimator theta hat is unbiased. So its MSE is simply equal to the variance of theta hat. Thus, for two unbiased estimators, comparing their relative efficiency, that is the ratio between the MSEs, amounts to comparing their variances. So the simple Monte Carlo estimator is a very convenient way to estimate the result of a definite integral. However, it has a few limitations. The first is that it cannot be directly applied to unbounded integrals. We have shown this last time, so there are two approaches that we can take for unbounded integrals. The first is to treat it like a bounded integral over a sufficiently large region, and maybe the tail, which is the rest of it, is just has a very small value associated with it. The other way is to apply change of variables in the integration and try to convert the unbounded integral into a bounded one. But none of them are very straightforward. The other drawback of simple Monte Carlo estimators is that it relies on uniform samples over a bounded region. So if the GFX function is relatively flat and even across the entire interval that we are interested in integrating over, then in this case, that's fine. However, if GFS has considerable variations over the interval a to b, meaning that if you see a lot of fluctuations in the function, then estimating theta by drawing from uniform a and b may not be very efficient. For these reasons, you might ask, can we improve the efficiency of our Monte Carlo estimator? Is there a better Monte Carlo estimator for these definite integrals that achieves higher efficiency compared to the simple Monte Carlo estimator? The answer is yes, and we will cover two methods for doing this. The first is known as importance sampling, and the other one is known as stratified sampling.